All right, welcome everyone. This is our final project review for crypto volatility intelligence. So what you're about to see is not just a train model, it's a full deployed monitor and rollback capable ML ops system. We'll walk through the architecture, our demo plan, how we handle failures, and what our numbers actually look like. Let's go into it. Next. All right, so this is the executive summary. We're gonna go more details into the next slides. So I'm gonna start with the problem. Why does this problem need more than a model? So volatility spikes in crypto markets are rare, short-lived events. A static threshold won't catch them in time, and a model predicting price direction is solving the wrong problem. The bigger gap, though, is that most course projects stop at training. We built the full pipeline, ingestion, feature engineering, prediction, monitoring, and rollback because that's what production system actually require. That's the framing for everything that follows. Next. So here the five state architecture. So the data flows from Coinbase WebSocket through Kafka into our future enduring layer, then through the FastAPI prediction endpoint, and out through a live dashboard and Grafana. Kafka is the key design decision. It decouples ingestion from inference, which means the model can be restored or swapped without touching the data stream. Every stage is independently observable through Prometheus. Nothing here is glued together in a way that breaks when one piece changes. Next.
Okay,
So I'm gonna offer to Rizaldi for the demo.
okay, thank you, Afif. So let's take a look at the how we bundle a project. We store everything in the GitHub, everything code and properly documented, and we have the release here. The version 1 release already have a zip code and also the source code here. And also we have a package here. We have a package which contain all the submission for the project, which contain ingestor, volatility API, ML flow, which flowing the model prediction, and also the dashboard. Now let's take a look how we can predict the data using the, the Docker. So for to running the Docker, we just need to using Docker Compose YAML, and also we can try to open this dashboard. So the dashboard connect to the API and also the Grafana dashboard. And this is the bonus dashboard that we built to connect all the artifacts. So as we can see here, the crypto price currently live from the Coinbase, it's about $77,000, and we have also Ethereum price. And this is the result from the modeling. We have AUC from logistic regression and also F1 score, which is already better than the baseline score. And we can open the Grafana from here. So the Grafana can show how healthy the system was, and also by request rate, and also by the prediction throughput, and also by inference latency. And we also previously model and also using industry standard, which is ML flow. In the ML flow, all the metrics is retained well. And we have all the model metrics here like F1, test F1, training score, and also AUC here. And this is industry standard as the model lives here as an artifact and can use for scalability and reusability. And beside Grafana, we also have like trend result here to make it shareable, and also model PR curve, and also the detail model evaluation here. So it can be accessed by everyone. And by the API, we can also see here how the system, is it healthy or not. And back to the dashboard, we can see all the chart here. So all the movement here is live for Ethereum and Bitcoin. And also we can see the artifact like when the volatile, it will predict model flag like the orange dot, and also all the model runs is properly logged here. So the dashboard is like the front end for all the system that we built for this project. Thank you. Moving on to the evaluation part.
All right. So on this model quality, our logistic regression beats the baseline Z-score model by 1.83 percentage points on a PR at AUC, and then 8.15 percentage points on F1 on a half-out chronological test split of 1,264 samples. In our case, logistic regression beats the baseline because the baseline is basically a single rule volatility dictator, while logistic regression can combine several weak signals at once. The baseline use discourse like it looks for unusually high volatility compared with the reference windows, and then the chronological split matters here, which reflects the actual deployment condition where the model only ever sees the past data. The F1 improvement is the more meaningful number for our use case, and the lower predicted positive rate, which is 4.4% versus 6.2, means the model is more precise. For a spikes alert system, false positive have a real cost, so that precision is better. Okay, next be explained by Jiho.
Thank you, Rido. For latency, we ran a burst load test with 100 concurrent post requests in week 5. All 100 succeeded, 0 failures. P50 was 74 milliseconds, P95 was 117, P99 was 122. The Prometheus histogram tells us that raw inference consistently stays within the sub 5 millisecond bucket. So the 50 millisecond mean HTTP response is almost entirely routing and serialization overhead. The model itself is not the bottleneck. Regarding uptime, our published SLO target is 99% availability over a 7-day rolling window. Next. To wrap up, here's what we achieved. We built a fully operational end-to-end pipeline from real-time data ingestion to live prediction and monitoring. The system passed load testing with 100% success rate and P95 latency around 117 milliseconds. We also implemented rollback and recovery mechanisms, and the model outperformed the baseline on both PR, AUC, and F1. The key takeaway is that this is not just a model, but a production-ready AI system that is reliable, scalable, and applicable beyond crypto. Thank you for listening.